In section 13.8, we focused on learning how to find maxima and minima of functions of two variables. We'd like to improve upon this concept and work with functions of two or three variables that are also subject to a constraint and to identify how to optimize those types of situations. So let's jump straight in and talk about the method of Lagrange multipliers. So what we're looking for is we're trying to find the maximum and minimum values of a function subject to some constraint equation. Now, before we move forward, I want to emphasize here that we have a function in terms of x, y, z on one side and the constant on another. So you're going to want to make sure that your constraint equation is written in that format. Step 1, find all values of x, y, z, and lambda such that the gradient of f is equal to lambda times the gradient of g, and such that your constraint equation holds. So this is really the only formula in this entire section that's new, something that we haven't seen. Again, the constraint equation here is just going to be given in the context of the problem. The number lambda in the above equation is called the Lagrange multiplier. Then we want to evaluate f at all points x, y, z that result from step 1. The largest value is going to be the max, and the smallest value will be the min. So very similar to what we were doing when we were finding absolute extrema on a closed and bounded region. We were finding critical points and we weren't using the second partials test. We were just plugging these values back into the original function and picking off the highest and lowest value. Same thing is happening here at step 2. I made a note here that this above method also holds for functions of two variables, even though I've written it in terms of three variables. So let's take a look at our first example. Find the maximum and minimum values of f subject to the given constraint, and find the points at which they occur. So we have our function x squared minus y squared, and then you see our constraint equation here. Notice that the x and y terms are on one side and the constant is on another. That is the appropriate setup. We want the constant on one side. And if we're going to write this in terms of our notation up above, we would say that g of xy is x squared plus y squared. All right, so let's go ahead and set up our equation here. We want to find where gradient of f equals lambda times gradient of g. So let's start here. The gradient of f is 2x and negative 2y equals lambda times next the gradient of g, which is 2x, 2y. So we can now set up a system of two equations. I have 2x equals 2x lambda, and I also have negative 2y equals 2y lambda. So let's zero in on this first equation. So long as x is not 0, what I can do is I can divide both sides by 2x and conclude that lambda equals 1. But again, it's very important whenever you're dividing by a variable, it's very important that you consider the case that that variable is 0. So I'm just going to make a note here. If x is non-zero, then that leads us to believe that lambda equals 1. And then similarly on the other side, if y is non-zero, then lambda is negative 1. So we'd like to analyze these two cases. Case 1, let's suppose that lambda is 1. All right, then the other equation, negative 2y equals 2y times lambda, which is 1, tells us that y has to equal negative y. And there's only one number that equals its opposite, and that's 0. All right, so we have concluded that if lambda equals 1, y must equal 0. What does x have to equal then? So we come back up to our constraint equation, which I just highlighted in orange, and we say if y is 0, then x squared plus 0 squared equals 25. And we conclude that x is plus or minus 5. All right, so our points here are plus minus 5, comma 0. So now let's take a look at our other case. Suppose now that lambda is negative 1. Now, if we look at our other equation that resulted from our gradient, we have that 2x equals 2x times 1. Negative 1. And so again, we have that x equals negative x, which forces x to be 0. Plugging into the constraint, if x equals 0, then 0 squared plus y squared equals 25. So y is plus or minus 5. So we get the pair of points 0 plus minus 5. All right, we have considered all the cases where lambda is 1, where lambda is negative 1, and furthermore, you'll notice that we even considered the case where y is 0 and x is 0. It kind of just happened in our analysis. All right, so this is the end of step 1. We have found all points at which both the constraint equation holds and that the gradient of f equals lambda gradient of g. So we found 4 points total, and now what we're going to do is we're going to evaluate f at those points. So we're going to test the function f of x, y at the above points. We have f of plus or minus 5, comma 0. First of all, remember our function was x squared minus y squared, so that's a 25 minus 0, which is 25. And let's evaluate also at 0 plus minus 5. So that's going to be 0 minus 25, which is negative 25. And so now our highest value is our max, our smallest value is our min, and so we conclude that we have a max of 25, and this occurs at plus minus 5, 0. We have a min of negative 25 at 0 plus minus 5. Okay, so there's our first example of working with Lagrange multipliers. This example was again a function of 2 variables. So for our next example, we'd like to look at a function of 3 variables. So let's take a look at number 10. We have a linear function 3x plus 6y plus 2z. And then we have the quadratic function, our constraint, 2x squared plus 4y squared plus z squared equals 70. Again, you'll notice that our constraint equation is in standard form where all of the variables are on the left and the constant is on the right. So that's always something you want to check. If you want to set up your g function, we have g of x, y, z equals 2x squared plus 4y squared plus c squared. All right, so let's get started. The one equation we have this section is that the gradient of f equals lambda times the gradient of g. So if we set it up, since f has all linear terms, our gradient is constant, 3, 6, 2, equals lambda times the gradient of g, which is 4x, 8y, and 2z. All right, now I want to note something right at this point. Note that lambda cannot equal 0. Otherwise, if lambda was 0, we would have that the vector 3, 6, 2 on the left would equal the 0 vector 0, 0, 0. Okay, so the fact that lambda is non-zero, and I just showed it was, means that I can divide things through by lambda. All right, so again, always keeping in mind, if I'm dividing by a variable, check if it can equal 0. So let me set up my system of equations. I have 3 equals 4x lambda. I have 6 equals 8y lambda. And I have 2 equals 2z lambda. So what I'm going to do in each of these situations is I'm going to solve for the variables x, y, and z. Again, I already checked that lambda is non-zero, so I can divide. So x can be written as 3 over 4 lambda. Y can be written as 6 over 8 lambda, which is also 3 over 4 lambda. And z can be written as 1 over lambda. Now remember, these points need to satisfy the constraint equation. So I'm just going to highlight that again to call your attention to it. What I know is these points, the point x, y, z, has to satisfy the constraint equation. So let's plug these expressions for x, y, and z into the constraint equation so that instead of 3 equations and 4 unknowns, we reduce it to 1 equation and 1 unknown. So plugging into constraint, we have the following. 2 times x squared is going to be 9 over 16 lambda squared, plus 4 times y squared, also 9 over 16 lambda squared, plus z squared, which is 1 over lambda squared, equals 70. Now to make my life a little bit easier, what I'm going to do is I'm going to knock out all the fractions by multiplying by a 16 lambda squared on both sides. So that's going to leave me with 18 plus 36 plus 16. And then on the right-hand side, I have 70 times 16 lambda squared. Now I'm just going to leave that as is, 70 times 16, and you'll see why here in a moment. So if I add up everything on the left-hand side, 36 plus 16 is 52, plus 18 is 70. So I have 70 equals 70 times 16 lambda squared. So no need to even carry out that multiplication because I'm just going to divide both sides by 70. And so I conclude here that lambda squared is 1 over 16. In other words, lambda is plus or minus 1/4. So important to include the plus or minus. If you forget about that, you're losing half of the points. All right, so make sure you include that whenever you square root both sides. All right, so let's look at both cases. Let's suppose that lambda is equal to 1/4. All right, then what we can do is we can get values for x, y, and z. And so x, when I plug in 1/4, gives me 3. Y is the same as x, so also 3. And when I plug it into z, 1 over 1/4 is 4. So here's my first point. Now let's look at the other value for lambda. Suppose that lambda is negative 1/4. We're going to get just the same point out, but with negative values. So our point x, y, z becomes negative 3, negative 3, negative 4. And now we just want to test our original function at these 2 points. Again, I'm going to zoom out so that we can see our original function up top. So I now want to test f of x, y, z at the above points. All right, so we have f of 3, 3, 4 to begin with. That's equal to 9 plus 18 plus 8. 9 plus 18 is 27, plus 8 is 35. And then f of negative 3, negative 3, negative 4, by similar reasoning, is going to be negative 35. All right, and so we can write out our conclusion. Let's zoom back in. Our conclusion is we have a maximum value of 35, and that occurs at the point 3, 3, 4. And we have a minimum value of negative 35. And that occurs at negative 3, negative 3, negative 4. All right, it just so happens that in both of these examples, the maximum and minimum were negatives of one another. That will not always be the case, but just happen to be the case in these two examples. All right, we have one more example here to finish out the section, but before we get to it, a common application of Lagrange multipliers is to minimize the distance between two objects. Now, we're familiar with the distance formula. We've been using it since chapter 11, but the distance formula is a little bit ugly because it deals with the square root. And the moment you introduce a square root into a function, then when you start taking derivatives, it just gets ugly quickly, right? It pushes the square root to the bottom, and then your gradient's going to be hideous, and we really don't want to go there. And so this is a super important remark here that's going to just make your life a heck of a lot easier. If you're trying to minimize or maximize the distance between any two objects, and this works in 2-space or 3-space, you can minimize or maximize the square of the distance function. So that is, by minimizing the square of the distance, it in turn minimizes the actual distance itself. So we can ignore that overarching square root, and we're going to use these two functions, depending on whether you're in 2-space or 3-space, as opposed to the standard distance formulas with the square roots involved. All right, so keep this remark in mind when you're working out homework. Whenever you're trying to optimize distance anywhere, use the square of the distance formula. And so our last problem is exemplifying exactly this. We have example, use Lagrange multipliers to solve the problem. Find the point on the line y equals 2x plus 3 that is closest to the point 4, 2. All right, so this problem is a little bit different than our previous problems because they don't explicitly write out the function that you're optimizing. We do have our constraint equation, which is right here. And so for my constraint, this is not in standard form. So to put it into standard form, what I'm going to do is I'm going to scoot that 2x over to the other side. I'm going to write it as negative 2x plus y equals 3. And that way I have the x and y variables on the left and the constant on the right. If you want to write out your g function, you would have g of x equals negative 2x plus y. All right. Now, what's the function that we're optimizing? That's always written as f of xy or f of xyz. And in this case, we're just going to be using the square of the distance formula up above. Now, instead of x naught, y naught, as it's written in the circled equation, I want to use the point that I am trying to be the closest to. So I'm going to set up my f of xy as x minus 4 quantity squared plus y minus 2 quantity squared. And so here's our function that we're trying to optimize. So now we're ready to set up our equations. Gradient of f equals lambda times gradient of g. So the gradient of f is 2 times x minus 4. The chain rule would kick out a 1, so I won't even write it. And 2 times y minus 2. So there's our gradient of f. And that equals lambda times the gradient of g, which is a negative 2 comma 1. So as usual, let's set up our system of two equations, equating the x components. I have 2x minus 4 equals a negative 2 lambda. And I have 2y minus 4. Whoops, and I just saw I made a mistake over here. Correct this 4. Let me do it in red. Correct that 4 to an 8. There we go. And then I have 2y minus 4 equals lambda. All right, so I have these two equations. Let's go ahead and solve for x and y. 2x equals negative 2 lambda plus 8. So x is negative lambda plus 4. And similarly, 2y equals lambda plus 4. Y equals 1/2 lambda plus 2. So we had no worries about dividing by a variable in this example. We only divided by non-zero constants. So now that we have expressions for x and y in terms of lambda, let's plug these expressions into the constraint equation. All right, so I have -2 times my x plus my y equals 3. So we're down to one equation, one unknown. Let's go ahead and simplify. I have 2 lambda minus 8 plus 1/2 lambda plus 2 equals 3. So I have 5/2 lambda equals 9. So lambda equals 18/5. So now that I know what lambda is equal to, I can take this value and plug it back in to my equations for x and y to come up with the point that must be closest. So plug lambda into x and y equations. And I have that x is -18/5 plus 4, which I'm going to write that 4 as 20/5. So I get an x value of 2/5. Y is equal to 1/2 of lambda, so that's 18/10 plus 2, which is 9/5 plus 10/5 for a total of 19/5. And so the point that we're looking for that is closest to the point 4, 2 on the line y equals 2x plus 3 is the point 2/5, 19/5. This concludes our notes over 13.9, which is also the culmination of chapter 13.